Have you ever stared into the infinite, trying to make sense of the pattern beneath the chaos? In mathematics, one equation embodies that mystery, the Riemann-Zeta function. At first glance, it looks simple, a sum over inverse powers of integers. But hiding in its heart is a structure so profound, it's said to encode the distribution of prime numbers and the fabric of number theory itself. And now, the quantum world may hold the key to unlocking it. Imagine a line, the complex plane, stretching out in all directions. Along it, mysterious zeros of the zeta function sit like pulses in the night, marking out a pattern that's resisted complete understanding for over a century. These zeros aren't just mathematical curiosities. They're connected to deep truths about randomness, cryptography, and even the very limits of predictability in the universe. But what if we could see them? Not with ink and paper, but with light and matter. What if the zeta function could be simulated? Enter Floquet theory. It's a framework for studying systems that change periodically in time. Think of a strobe light flashing rhythmically over a dancer. In the quantum world, this kind of periodic driving can generate entirely new energy landscapes, known as quasi-energies, where exotic behavior like topological phases and time crystals emerge. Now imagine trapping a chain of ions, atoms stripped of electrons, in an electromagnetic well. These ions can act like quantum bits, or qubits, and we can control them with pulses of lasers and microwaves. By periodically driving them with carefully timed fields, we can create a Floquet-engineered system where the energy levels, the resonance patterns, start to mirror the structure of the Riemann-Zeta function. Each ion becomes a tiny window into the mathematics of infinity. What's truly incredible is that the zeros of the zeta function, the ones lining up on the so-called critical line, may correspond to resonances or dips in the energy spectrum of this driven quantum system. It's like tuning a guitar string and hearing silence when you reach a hidden frequency. That silence corresponds to a zero of the zeta function. But there's more. These simulations don't just reveal abstract math, they demonstrate something deeper about our universe. That even the most elusive concepts in pure math, long thought to live only in theory, can take on physical form in a quantum system. And here's the twist. Room temperature systems, like NV centers in diamond or superconducting qubits cooled with mere liquid nitrogen, might also support this kind of mapping. We could, in principle, walk into a lab, flip on a switch, and watch the zeta function come to life on a screen. Not numbers, but interference patterns, photon emissions, and qubit states. It's mathematics made physical, a dream of the Pythagoreans, realized through physical quantum simulation. So what does this mean for the future? It blurs the line between theory and experiment, between number and nature. It means that mathematical mysteries might no longer be solved only with chalk on a board, but by running an experiment, watching how quantum particles move, seeing math unfold in time. As we build better quantum computers and simulators, the zeta function may become just the beginning. We might simulate modular forms, L functions, even the structures of space-time itself. And maybe, just maybe, one day we'll watch the Riemann hypothesis, one of the deepest unsolved problems in mathematics, collapse not with a proof, but with a measurement. This is the frontier, where math meets matter, where light reveals logic, and where the secrets of infinity are whispered by qubits.